Welcome back, everyone. In previous slide, we have covered what is full annealing, how it is will be useful for the different kind of steel, that is a hypoelectric steel, hyperelectric steel, and the electric steel. So, in brief, hypoelectric steel and electric steel, we are using this annealing treatment, but it's not that much favorable to use for the hyperelectric steel. Okay. Next annealing heat treatment is isothermal annealing. Yeah, as the name indicates, isothermal annealing, it's a constant temperature annealing. I will explain why it is called as an isothermal in this video lecture. First of all, we are considering the hypoelectric steel and heating above the upper critical temperature, that is the A3 line, as I mentioned in the previous slide, and we are heating this for the longer duration of time as because we should get the uniform temperature gradient, and when we will get the complete austenitic structure, the homogeneous austenitic structure, we will start to cool down. This is a cooling suddenly to a temperature of about 600 to 500 degrees Celsius. This is a sudden process. This can be achieved by transferring the sample from one furnace to the another furnace with a temperature of 600 to 500 to 600 degrees Celsius. Initially, it was more than upper critical temperature. Then it should be lower critical temperature. We have to hold this sample at this temperature until all the austenite should be converted into perlitic region. After when ensuring that all the perlitic regions are formed, all the austenite transformed to perlitic region, then it is used for the cooling. This is the final microstructure is we are getting is perlitic region completely. This is used for getting the more ductile and machinable products such as pellets. Okay, this is for the hypoelectric steel. Whereas for the eutected steel, we are heating. We in this main aim is to get the uniform austenitic structure. For eutected steel, we will get the austenitic structure just heating above the A1 line. That is a lower critical temperature. So we have to heat similarly and hold it for the longer duration of time so that we can get the complete austenitic, uniform austenitic size, and then again similar process carried out which is carried out for the hypoelectric steel. We have to lower its temperature, lower the temperature such that we should get the temperature about 600 to 500 degrees Celsius, lower than the lower critical temperature. Then hold it for the same duration of time to get the complete perlitic structure. Then it is cooled down. Similar, this is a eutected steel. The prefix isotherm is associated with the annealing implies that the transformation of an austenite takes place at a constant temperature. See, this is the constant temperature process. Here it will be the austenite, and at the end of this one, here it is perlitic region. This is at a constant temperature. Hence, this is called as an isothermal annealing. So you may ask the question that we are getting the perlitic region in the annealing, full annealing also. So what is the reason behind to use this isothermal? The reason is it's a cost effective. It's a cost effective process. It's a shortcut process. The time duration to get the perlatic region is very small as compared to that of the full annealing. In full annealing, we are heating above and we are doing very slow rate of cooling. So if you do a very fast rate of cooling, there may be a chances of getting the internal stresses. Then there is no use of that heat treatment process. But whereas here there is no such a hard and fast rule that we have to cool it very slowly or very fastly. There is a minimum rate of cooling will be there to maintain that perlatic region. Here the products also very effective and to get the perlatic region. That's why the most to you if you want to remove the internal stresses and increase the ductility property, so we most of the researcher will use isothermal annealing. This process not only improves the machinability in general but also results in the better surface finish by machining. The process is of great use for alloy steels as these steels have to be better cooled slowly. This is all about the isothermal annealing. Okay, next type of annealing is diffusion annealing. So in this annealing process, we are removing the non-homogeneity in the structures. I will explain in detail. For example, if there is a structure which is having some dendritic structures, this is a dendritic structures, means it is having non-homogeneity. There is no uniform distribution of the composition. So by this diffusion annealing, we will get the homogeneous distribution of the structures. These are the grains, which is if you measure the compositions of an alloy, for example, this is if you measure the composition of an alloy is different here in dendritic region is totally different. But whereas after this diffusion annealing, if you measure the compositions throughout the sample is same. In this process, the elements present in this one they will diffuse each other at that temperature and make them as a uniform distribution. Hence, the steel is heated sufficiently above the upper critical temperature and held it for the prolonged duration of time for 10 to 20 hours, followed by slow cooling, results in the formation of uniform distribution. Why we need to heat sufficiently above the upper critical temperature? This is sufficiently above the upper critical temperature is means 1000 to 1100 is the temperature where we are heating. This is the highest temperature used in the annealing process. That is a diffusion annealing, because the material has to diffuse. To diffuse this one, we need to give the some external thermal energy to diffuse in the another material. It requires more activation energy. That's why we are heating the at a very higher temperatures. So, what is the side effects? Side effects of this non-homogeneity in the structures? Please mention in the comment box sections. So, why need to get the homogeneous structure? Why not this? Why we are not using this non-homogeneous structures for the normal day-to-day applications? Please mention what are the side effects, the disadvantage of the non-homogeneity in the structures. Okay, next heat treatment process is partial annealing, and this is also called as an intercritical annealing and the incomplete annealing. In this annealing, this is, as we said in the previous annealing process, the hyper-retracted steel are not suited for the previous annealing processes because it will give a microstructure which is having which which is having poor mechanical property. But this annealing heat treatment will use it for the mainly for the hyper retracted steels, but we won't get the network like structures of the cementite in the microstructure. Instead, we are getting the uniform distribution of the cementite as well as the ferrite we will get, and perlite we will get, and which is having a better mechanical properties than any other microstructures are subjected to this heat treatment. The final microstructure consisting of a fine perlite as well as the cementite. This finer, the perlite, if it is a finer perlite, we will get a more good mechanical properties. Here, the heating temperature is plays a very important role because we are heating just above the A1 line and below the A3 line. This will result in the uniform distribution of the perlite as well as the alpha ferrite and the cementite. And when we will started the cooling uniformly, we will get the perlitic structures, fine perlitic structures along with the cementite. And this heat treatment can also be employed for the hyper-retracted steel, which is helpful for the improves the machinability. But usually we won't use this heat treatment process, partial annealing process. Instead of that one, we can use the full annealing process or isothermal annealing process. So many processes will be used for the hyper-retracted steel as well as the retracted steel. In brief, this partial annealing process used for the hyper-retracted steel. Okay. Next is very important annealing process and most widely used in the industries. That is recrystallization annealing. Okay, recrystallization annealing, we will get a new grains. This is employed only for the heavily deformed, heavily cold work and heavily deformed materials. This recrystallization annealing is a heated above the recrystallization temperature and hold it for the some time, and then it is same cooling results in the formation of new grains. This will result in the decreasing in the hardness and increasing the ductility. The hardness and ductility are inversely. If we are compromising with the hardness, then the ductility is improved. And the final product that we are obtaining for this from this heat treatment is a strain-free grains are produced from the expense of deformed original grains. This recrystallization annealing mainly depends upon the composition and prior deformation. How this deformation will affect, I will explain now. And the size, initial grain size, this deformation rate is affecting the final grain size. If you want to get a finer grain size, smaller grain size, we need to have the heavily deformed microstructure, heavily deformed samples. If this deformed structures will helpful for to getting the nucleating the new grains, nucleation. These are nucleation sites. They act as a nucleation sites, and hence the new grains will be generated at this sites and results in the finer grains. And these finer grains will have the more good mechanical properties. High carbon steels and the alloy steels are require the higher recrystallization temperature as compared to that of the low carbons and the low carbon steels. Here the recrystallization temperature will also plays a very important role in the recrystallization annealing. These recrystallization grains microstructure is having stress free, new grains are formed. This is the method of enhancing the mechanical properties without adding any external component. So in a composite material we are adding some of the particles or precipitation particles we are adding to enhance its mechanical properties, but here just by the heat treatment process itself we are enhancing the mechanical properties. So in so many interviews they will ask a question, how you will enhances the property of the material without adding any component, any external alloying element. This is the heat treatment process. There is a recrystallization heat treatment process is a good example for this one. Okay. Next annealing process is process annealing. In process annealing, we are heating below the critical temperature, lower critical temperature, and hold it for some time, and then it is a cooling with a slow rate. Since it's subcritical annealing, the cooling rate is very important in this process. This heat treatment will reduces the similarly hardness as similarly in the case of the recrystallization annealing. Here but there is no change in the microstructures because we are heating below the lower critical temperature. It is totally different from the in the sense different from the recrystallization annealing. Here there may be a chance of getting a new grains completely, may or may not. That means we will get a new grains or we will get we will get grains, new grains or not. It's not a confirm in this process, but it's a low cost compared to that of the recrystallization because we are heating in the lower temperature. Hence, it's a low cost and more affordable process annealing. Last, I will explain whole this different type of an annealing with a different temperature range. First of all, I will start with higher temperature. As I explained, more temperature is required for the diffusion annealing. This is temperature ranges 1000 to 1200 degrees Celsius. This is the highest one because we need to diffuse the elements. And whereas for the full annealing, it's about 30 to 50 degrees Celsius above the A3 temperature. And whereas for the partial annealing, we have just heated the A1 temperature. Then partial annealing used for the hyper-eutrophic state. And whereas a recrystallization annealing and here the process annealing. Recrystallization annealing is also much lower than that of the A1 temperature. Here it is similarly in the case of the process annealing. We will get the new grains. the older deformed grains are transformed into the new grains. Whereas here we may not get the new grains, but there is a we can remove the internal stresses and other things we can remove and increases the ductility property. Property from this process annealing process. Okay, this is overall annealing heat treatment process, and in the upcoming video lecture we are knowing about the different kind of annealing heat treatment process such as spheroidization, normalizing, tempering process, etc. Okay, so if you have any doubts, please mention in the comment box sections and let me know. Thank you.